In this first lab, I studied constant velocity and its relation to Newton's second law and the momentum principle. The purpose of this lab was to observe and better understand the relationship between velocity, acceleration, and net forces, and the specific implication of an object's velocity being constant. In order to complete this lab, I compared the observed motion of an object that supposedly had a constant velocity, which was analyzed using tracker software, with a computational model of the predicted constant motion of the object that was made with PHYS. I then compared the experimental and computational data through Excel and created a line graph to visualize both the predicted and observed motion. Although Newton's second law and the momentum principle come to the same conclusion, I will refer to Newton's second law throughout this report. Newton's second law states the following: net force is equivalent to mass times acceleration. Since acceleration is defined as the change in velocity divided by the change in time, net force is equivalent to mass times delta v over delta t. This principle was then applied to update velocity and position iteratively using the velocity and position update formulas. The comparison of my observed and predicted data showed that although both the experiment and model had a pretty constant motion and velocity, the predicted velocity was higher than the observed, which is a result that I will explain further later on in the lab. The first step in performing this lab was to identify the system and surroundings. My system is a low-friction cart located in my lab section's classroom, and the surrounding is a frictionless track that the cart rolled along for the duration of my observational video. For the experiment, a group mate of mine pushed the low-friction cart and I recorded its motion for a period of time. I then cropped the video slightly after the cart left my group mate's hands in order to account for and negate the initial increase in velocity that occurred since the cart was originally at rest. I then used the tracker software to obtain data about the motion of the cart. I calibrated distance by using the ruler on the frictionless track, and I oriented the axes/coordinate system to be parallel with the track with the origin at a black mark on the cart. Then I went frame by frame through the video and updated where that black mark was each time to track the updated position at each time. This line graph and chart were generated. According to the data, this is the initial position, and I calculated the initial velocity by subtracting the initial position from the position at time t equals 0.016 seconds and dividing that by delta t of 0.016 seconds. This gave me this initial velocity vector since the movement of the cart only occurs in the x direction. After obtaining this data, I transitioned to Web v Python to create a computational model of the predicted motion of my cart. Using the start code provided, I input the initial conditions for position and velocity that I just found, and then I changed the velocity and position update formulas to reflect what I previously described. I also added the mass of the low-friction cart, 0.5 kilograms. However, it ended up being inconsequential. Since this lab is looking at constant velocity, the change in velocity should be 0 meters per second and the acceleration should likewise be 0. Translating this to Newton's second law, that means that the net force would also be the 0 vector, which I input. The velocity of the cart will never change since Fnet is 0, so the mass of the cart does not matter. After running this code, I used its data for my Excel comparison. Again, here are the results of my experimental data and computational model comparison. They are both similar in that the object moves at a constant velocity for both, which we can tell because each line on the graph has a constant slope. However, the slopes are considerably different and the computational model's velocity is higher than that of my experimental data. I think this may be due to human error with tracker because as I clicked on the same black mark frame by frame, I probably didn't always click at the exact same spot of the black mark, which decreased the accuracy. Since the initial velocity I calculated was only based on the first 2 data points in tracker, the computational model was formed using that velocity, which was actually a little bit higher than the average velocity of the entire experiment. If I flipped the x-axis so that the positive and negative x's were switched, the low-friction cart would have been moving in the negative x direction, and my graphs would have shown the object moving in that negative x direction over time, as opposed to the positive direction. The velocity would have remained the same in magnitude, but it also would have become negative. It is not possible to say how many pushes and pulls or how many forces are added together to create the case that I observed in this lab. The net force only gives us information about the sum of all the forces, but we do not know how many forces were summed together, nor the magnitude or direction of all of the individual forces. All we know is that certain forces like the force of gravity and the normal force exist, and that they all add up to 0 newtons, which causes 0 acceleration and the constant velocity.